Today I'm going to be talking about presenting my research on carbon dioxide utilization to produce concrete and whether there's a significant climate benefit from utilizing captured dioxide to produce concrete products. Uh, Before I start off, so I'm part of this bigger team at the University of Michigan with collaborators like Dr. Keoleian, Dr. Miller, Volker, Victor Lee, and Zhang. I work at the University of Michigan. So, what's motivating this research on a circular economy for carbon dioxide? Well, this is the linear model that we see usually that happens. We have a lot of manufacturing industrial activity going on, and emissions, carbon dioxide emissions, and other greenhouse gases that get emitted, and that poses the challenge of climate change. So in order to address this, one of the emerging pathways which is widely discussed is a circular economy for carbon dioxide itself. Circular economy needs no introduction, but this specific field of not just sequestering carbon dioxide, but actually capturing carbon dioxide and making commercially valuable products like chemicals, polymers, fuels, concrete. It offers the twin benefit. One is you're having the obvious environmental benefit of preventing or slowing down climate change because you're capturing and utilizing carbon dioxide. The second obvious benefit is economics. So if you're able to reduce costs and produce products from carbon dioxide which are cheaper than conventionally produced products, then we have a twin benefit. It's not just environmental benefits, but also economic benefits. With this in mind, why do we need to focus? Why is that we need to focus on concrete or cement? Cement is one of the materials, it's one of the key ingredients in concrete. So why is it that carbon dioxide utilization for producing concrete is a promising idea? You can see the graph here. On the left, we have this pie chart. This was a study in science. It shows that concrete cement accounts for almost 5% of the global CO2 emissions. That's probably, it ranks 8th or 9th in terms of country-wise. So if concrete or cement production is a country, it'll rank 8th or 9th in the world in terms of CO2 emissions. So that's a pretty big contributor to global climate warming. And more importantly, the study also pointed out that not only is it a big contributor to climate change, but it's also one of the hardest sectors to decarbonize. The nature of the production processes for cement, which is required in concrete, makes it very hard to decarbonize. So this study also rightly mentions that cement is pretty hard to decarbonize. So there is a lot of environmental motivation to decarbonize concrete. And one of the ways of doing this has been another report from the Chatham House. Carbon capture, sequestration, and utilization is identified as one of the emerging pathways to capture carbon dioxide and use it in concrete production to decarbonize the concrete sector as such, because worldwide we know that cement consumption, concrete consumption is increasing rapidly. In fact, I think after water, concrete is the most commonly used material in the world. So in terms of scale, in terms of the problems it poses to the environment, carbon capture and utilization is a great option to address climate change in the concrete sector. And it's been increasingly viewed so by experts. In fact, if you look at a couple of emerging reports and scientific studies, concrete has got a great potential to sequester carbon dioxide. As you can see over here, this circle over here, it says that around 0.6 to 1.4 gigatons of carbon dioxide can be utilized in the concrete industry, and estimates show that there's a significant amount of economic interest too if this industry can be established, around $15 billion to $150 billion. It's still early days, but there is a lot of promise. We have to keep that in mind. It's not an established industry utilizing CO2 for concrete, but there's a lot of interest in it. In fact, this study in Nature in 2019 showed that there is significant utilization potential in the concrete industry. And from a scientific point of view, carbon dioxide, once it's sequestered in concrete, it's a very stable molecule because it becomes a carbonate, either calcium carbonate or magnesium carbonate or silicates. So it's a very stable molecule, and it's sequestered for quite some time, for the lifetime of the building material, more than 60 years. So also from a thermodynamic perspective, it's a great option to capture and utilize CO2 in concrete. So I've talked about certain initial reports, commercial reports and trade reports and some scientific papers. So now getting down to the technical side of things, there are a lot of studies which investigate the material properties of concrete that is manufactured from captured carbon dioxide. I've given you a screenshot of a couple of studies over here. In fact, there are around 99 experimental data sets from 19 studies that report findings on carbon captured and utilized concrete. I'm going to use this abbreviation. CCU concrete is for carbon capture and utilization concrete versus conventional concrete. So a lot of studies have investigated how CCU concrete functions with respect to conventional concrete. The underlying assumption for this entire body of research is that by utilizing carbon dioxide in concrete, you're producing a climate benefit. However, it's important to understand that this is an emerging technology and we have to rigorously understand whether the claims are actually backed up by actual evidence. So there are a lot of shortcomings in terms of carbon capture and utilization of concrete production. In this research, we looked at what the shortcomings were. A lot of broad life cycle considerations when evaluating the climate benefit of CCU concrete, they were not considered. There's a lack of consistent assumption, system boundaries, inclusion, exclusion of processes while quantifying the climate benefit. In short, there's a lot of inconsistency in the assumptions. And also given that this technology, carbon capture and utilization for concrete production, it's an emerging technology, there's not much of robust analysis of the impact of uncertainty, because as we all know, in the early stages of technology, there's a lot of uncertainty in data, material and energy inventory data, which is required to run the life cycle assessment and understand the climate impacts of any specific product, more importantly, in terms of carbon capture and utilization. So these are some of the shortcomings. So with this background with respect to the shortcomings in the technical studies, we set out to answer the following questions in this research. So the first major question is, will replacing conventional concrete with CCU concrete produce a climate benefit? So tomorrow, if the world were to transition from conventional concrete to CCU concrete, will it actually produce a climate benefit like a lot of studies claim? If so, what are the key drivers of the climate impact of CCU concrete production? So whether it be a climate burden or a benefit, what is it that's driving the climate impact of CCU concrete production? And the third question is, what is the impact of the data uncertainty on the findings? As CCU is an emerging technology, we need to account for data uncertainty when you're doing a life cycle assessment. So these were the broad set of questions that we wanted to answer in this research. So if I have to explain this research in a very conceptual basis, so we have conventional concrete production on the left of the screen and CCU concrete production on the right of the screen. So if you're going to look at conventional concrete production, the concrete production happens separately over here. I hope you can see my mouse. We don't have carbon capture in the plant, so CO2 gets emitted. Now we can have an alternate system where we're actually going to capture the carbon dioxide from the power plant and utilize it to manufacture concrete. So over here, we have 1 MPa of concrete. I'm going to use the function unit of 1 megapascal of strength for the concrete that is produced. So these are the two systems that we'll be comparing in this study. And so in order to quantify the climate benefit, I'm going to use this metric, the net CO2 benefit. So the net CO2 benefit effectively is the life cycle CO2 emissions of CO2 emissions from production of conventional concrete, minus the total life cycle emissions from CCU concrete, that is carbon utilization concrete. So if this benefit is positive, that means CCU concrete is less carbon intensive than traditional conventional concrete, and therefore we are producing a climate benefit. However, if the net CO2 benefit is negative, that means CCU concrete is actually increasing climate impacts and it's more burdensome than conventional concrete from a CO2 perspective. So this is a broad conceptual explanation of what I'm going to do in my research. And I won't get into the nitty-gritties of the processes that we have considered for CSU concrete production. Briefly, we have the set of materials that is required to produce concrete in gray, and we have in green the steps that are required to capture carbon dioxide from a power plant. Uh, then we have to transport it, vaporize it, inject it, and use it in either curing or mixing of concrete. So there are two ways in which we can use carbon dioxide in concrete. We can either use it in the curing process or in the mixing process. It's also important to note over here that when we are capturing carbon dioxide in a power plant, that itself requires energy. So there is an energy penalty that is incurred at the power plant, because in case CO2 was not captured, the power plant will be producing more energy. But because CO2 is required to be captured now, we are introducing an energy penalty, and we need to turn on an external plant to compensate for this energy penalty called EP. So these are recommendations from NETL. I'll be using NETL recommendations in this study. So the functional unit I'm going to introduce is 1 megapascal of compressive strength of concrete and energy penalty of EP kilowatt hours of electricity. So these two will be the functional unit in this life cycle assessment. So in sum, there are 13 processes covering the production of materials and the capture and utilization of carbon dioxide to manufacture concrete. They are numbered P1 to P13 in this study. So there are 13 processes that need to be considered. The alternate system is we have the power plant which produces EP kilowatt hours of energy without carbon capture. So all the CO2 is emitted into the atmosphere, and we have conventional concrete that is being produced separately. So we are going to compare these two systems. So I'm going to use this graph. This will be the first set to understand if there is a net CO2 benefit of concrete. So on the x-axis over here, I'm plotting conventional concrete minus CCU concrete, the CO2 emissions. So as I explained, if it is positive, that means there is a benefit. It will be in the positive x direction. If it is negative, that means CO2 emitted from CCU concrete is more than what is emitted from conventional concrete. So as we have accounted for uncertainty, the results of the net CO2 benefit is going to be a distribution. In this case, the left of the y-axis, that is, it's entirely in the negative x direction. So that means in 2000 Monte Carlo runs, there is a 0% probability that CCU concrete is going to produce a climate benefit. So this is how I'm going to interpret these results. So we repeated this study for 99 data sets that we got from the literature. So we got this from literature, 99 data sets from literature, and we ran this mathematical model. And it's important to note that if the background is red, that means CCU concrete is more burdensome than conventional concrete in terms of the climate impacts. And if it is green, it's CCU concrete is producing a climate benefit. And this percentage, as I told you, is the likelihood of it producing a benefit out of 2000 Monte Carlo runs. Over here, it is 0%. When we repeat for the 99 data sets, I won't get into each of the data sets. So when we repeat analysis, the 99 data sets, what we get is that 51 out of the 99 data sets, CCU environmentally more burdensome. It increases the climate benefit. It increases the climate burden. So it's better concrete than use carbon capture concrete. So that is a problem when we're going to expand analysis to the 99 data. Note that CCU concrete does not always sequester CO2 from a life cycle perspective. It's almost a 50-50 probability that it increases the climate burdens when compared to conventional concrete. So we wanted to understand, as I told you, there were 13 process parameters that we considered in this model. We wanted to understand visually what is it that's driving the net CO2 benefit. What's the most important process parameter driving the difference between CO2 emissions from conventional and CCU concrete. So on the x-axis over here, we have plotted the difference between CO2 emissions from a specific process in conventional concrete and the same specific process in CCU concrete. And on the y-axis, we've seen what we plot the net CO2 benefit, that is the total CO2 emissions from conventional concrete minus the total CO2 emissions from CCU concrete. So the visual inspection will be the first step of analysis. We did this for all the 13 process parameters that I just described in the previous slide. As you can see over here, the purple dots over here are pretty, in this scatter plot, they seem to be very dominant. The purple dots correspond to the consumption of OPC. OPC is nothing but cement, ordinary Portland cement. So that seems to be driving the net CO2 benefit. In this case, the background of the graph is red. So it means that in this specific data set, CCU concrete is more burdensome in terms of climate impact when compared to conventional concrete, and OPC is the key driver. The amount of cement consumed in OPC, in CCU concrete, and the amount of cement consumed in conventional concrete, the difference between those two is driving the net CO2 benefit, which shows that CCU concrete is more burdensome than conventional concrete. So we repeated this step of analysis for the 99 data sets. And what we get is that the three patterns, three key findings from the 99 data sets. Initially, a visual inspection shows that of the scatter plots, the amount of cement consumed, the amount of energy required to cure with CO2 in CCU concrete, and the amount of supplementary cementitious materials, that is materials apart from ordinary Portland cement, which is used as binder materials, in orange. So purple, black, and orange, as you can see here in most of the graphs, they are the most important parameters, 3 out of the 13 parameters that are most important. They have a significant influence on the net CO2 benefit. So this is just a preliminary analysis, a visual inspection, but it's not quantitative in nature. So we went a step ahead and we conducted a moment-independent sensitivity analysis, where we actually run a sensitivity analysis to calculate a delta index value for each of the 13 parameters. As you can see here, this is how we'll interpret this graph. The parameters with the highest delta index, this delta index is calculated using a moment-independent sensitivity analysis. The parameter, the highest delta value, has the greatest influence on the net CO2 benefit. As you can see here, purple has got the highest value. So that means OPC consumption has a significant influence. And if it is in the negative direction, negative X direction, that means the consumption is higher, or the parameter value is higher in CCU concrete when compared to conventional concrete. And as you can see, the background is red. So that means because OPC consumption is higher in conventional concrete when compared to, is higher in CCU concrete when compared to conventional concrete, CCU concrete tends to be more burdensome in terms of climate impact when compared to conventional concrete. So this is how we interpret the graph. If it is negative direction, the parameter is higher for CCU concrete. If the bar was on the positive direction, that means it's higher for conventional concrete. So we ran this quantitative sensitivity analysis for each of the 99 data sets. And what we discovered kind of validated what we saw in the scatter plot analysis. OPC consumption is a key driver. Cementitious, supplementary cementitious materials, that's another key driver, and the amount of energy you use in CO2 curing. And out of the 99 data sets, in 51 data sets, using carbon dioxide to produce concrete actually increases climate burden. And the reason for that, the key reason for that is when we use CO2 to produce concrete, it reduces the amount of compressive strength of concrete. So therefore, CCU concrete has lower compressive strength when compared to conventional concrete. In order to compensate for the loss in compressives, we need to increase cement consumption or SCM consumption. Cement is the most CO2 intensive material in concrete. So therefore, if you're going to use more cement, we are going to introduce significant life cycle CO2 burdens. So as I mentioned here in this point that is in bold, the life cycle CO2 emissions from increased cement consumption outweighs the benefit of actual CO2 utilization to produce concrete. So it's very important to emphasize that we need to look at these emerging technologies from a life cycle perspective, especially given that out of 99 data sets, we discovered that in 51 data sets, utilizing CO2 to produce concrete tends to increase climate burdens. So if I have to summarize, so what can be done about this? Future research, we need to actually look at the material properties of CCU concrete and ensure that when we're using CO2 in concrete, the compressive strength of concrete does not decrease. Either it remains the same or it increases. Only then can we conclusively claim that there is a climate benefit from utilizing CO2 in concrete. And in addition to that, we need to understand that we need to reduce energy requirements in the curing process itself. So these are some of the steps that material scientists in the concrete field can pursue in order to reduce the climate impact of CCU concrete. So in summary, out of 99 data sets, 51 CCU concrete tended to be more burdensome. There is no conclusive evidence to state that CCU concrete will always produce a climate benefit when compared to conventional concrete. Loss of compressive strength is a key concern, and future research should look into avenues so that we don't lose compressive strength when we're using carbon dioxide to produce concrete. That'll help improve the climate benefits from CCU concrete. So those are some of the future steps that need to be pursued. With that, I'd like to thank the Global CO2 Initiative at the University of Michigan for supporting this research and all my colleagues at the University of Michigan. Thank you, and I'd like to open up the session for questions.
Thanks, Derek. It looks like we already have 3 questions in the chat.
Okay.
The first one is from Birdie. Birdie, do you want to do you want to speak up? About
actually, yeah, thank you. This was a great presentation. I'm very much interested in seeing your publication. I think you may have actually answered my question in terms of attribution to cement versus concrete in general. So thank you for that.
Yeah. It's currently in review, so in Nature Communications.
So we have, it looks like we also have a question from Mick. Mick, do you?
Yeah. Sorry, I'm assuming that OPC is some term for Portland cement. Can you tell me what OPC is?
Yes, ordinary Portland cement.
Ordinary Portland cement. Okay, great. And then the second question is the last one here that I've recently been talking to Carbon Cure, and their website and their staff have said that injecting CO2 into concrete actually increases the strength of the concrete and also displaces the need for cement, reduces the need for cement. So are they talking about a different process than you're talking about here?
No, definitely. So that's the reason we actually ran this analysis for all the 99 data sets that are published in scientific literature. In certain conditions it does, and that's the reason it's in green, as you can see over here. Can you see the slide?
Yes.
Yeah, so for example, in this study number 5, it's in green. That means CCU concrete is actually beneficial to the environment, but because compressive strength increased and therefore concrete cement consumption reduced.
Okay.
So what we are saying is that it's not, the evidence is inconclusive, 51 out of 99. So there are a lot of steps that need to be addressed. It's not always the case.
Okay, got it. All right, thank you.
And the last question.
In fact, we had a couple of studies. Yeah, we had a couple of studies from Carbon Cure as a part of this study, which were reported in literature.